Okay, so let's now look at specific heats for gases. And so in this graph here, we have a PV diagram. This is pressure here, this is volume, and there are two processes here, process A and process B. Process A is an isochoric process, so you go from this initial state to this final state without changing the volume. So you're heating the system here and the pressure is increasing as you go up. So you go from an initial temperature I to a final temperature F. This process V is an isobaric process. Here the pressure is constant. So you are expanding the system, but at the same time you're heating the system. So you're adding heat to the system, and at the same time the system is doing work. And you go from an initial temperature to a final temperature. Now, if you look at this, these red lines, these are isotherms. So you can see that both systems, they start at the same temperature and they finish at the same temperature because they finish at these isotherms. So what is the change in thermal energy for these two systems? Well, process A and B, they both have the same delta T, right? Because they start at the same initial temperature and finish at the same final temperature. Because this is an ideal gas, then they also have the same change in thermal energy. However, you require more heat to produce this process than to produce this process. This process here, the isochoric process, requires less heat. Why is that? Well, because you're adding heat here, but some of that heat is being used to expand the system, and the system is doing work as you add heat. So not all the heat that you're adding goes into the thermal energy of the system. Some of it is going to be used to do this work, this expansion work. So the total change in energy for any process due to work and heat is for an ideal gas, for ideal gas, right? Anytime there is a change in temperature, anytime there is a change in temperature, the change in energy of the ideal gas, right, or delta U, that is equal to the number of moles times the molar specific heat at constant volume, and we'll define that in a little bit, times delta T. This is always true. So these are two different processes here. This is a process at constant volume and this is a process at constant pressure. So it's going to be useful to define a specific heat at constant volume for this process and a specific heat at constant pressure for this process. It is just a convenience, and so it is useful to define two different versions of the specific heat, constant volume and constant process. We're going to use the molar specific heat because most of the time we'll be using moles. And the quantity needed to change the temperature delta T of n moles, so if you want to change by delta T n moles of a gas, and if you want to do that at constant volume, then the heat that you need is equal to the number of moles times the specific heat at constant volume times the change in temperature. Uh, if you want to do that at constant pressure, then you need this much heat, which is the number of moles times the specific heat at constant pressure times delta T. In both cases, in both cases, the change in thermal energy is equal to NCV delta T. However, in this case here, for constant pressure, there is the added work that the system is doing as it expands, and that added work then makes that here you would have delta E thermal is equal to Q plus W. So there's no W for the constant volume process, but there is work for the constant pressure process. So both processes have this change in energy, and this is always true for any ideal process, but the heat added are different for each one of the process. CV is called the molar specific heat at constant volume. CP is called the molar specific heat at constant pressure. These are tables for specific heat for gases. This is helium, neon, argon, and these are diatomic gases, and H2, hydrogen, nitrogen, and oxygen. So this is the molar specific heat at constant pressure. They are pretty much the same because they are ideal gases. Here they change a little bit. These are the specific heats at constant volume. And the nice thing, notice this, notice what the quantity Cp minus Cv gives you. If you take Cp minus Cv, you get 8.3 in all cases. 8.3 is that constant that we get in the ideal gas equation. Pv is equal to nRT. So that R, which is 8.31, that is Cp minus Cv for all gases. Okay, so we have a question here. We have 1 mole of air and it is at an initial temperature of 20 degrees Celsius. Then I add 200 joules of heat isochoric in an isochoric process, right, at constant volume. And then remove 200 joules of heat in an isobaric process. What is the final temperature? Is it less than 20 degrees, equal to 20 degrees, more than 20 degrees, or not enough information? Take a minute to answer the question. And it is more than 20 degrees. Why? Well, because you're going to take, you have an initial temperature, which is 20 degrees. So you're going to take your system from Ti to a final Tf, right? And in here you add 200 joules of heat, and you do that in an isochoric process, right? So all that heat goes into the thermal energy, right? So delta E thermal is equal to NCV, and I have CV here, which is, as I saw in the previous slide, it is 12.5, right? So I have E thermal here, right? NCV delta T, which delta T is TF minus TI. So now in the reverse process, I'm not going to go all the way to TI. I'm going to go somewhere here, right? Why? Well, because some of the heat, I'm removing 200 joules of heat when I go down in this process. But some of that heat, this is an isobaric process, the system is going to be compressed as I remove the heat. So basically two, the 200 joules are not all heat. Some of it is the work that is being done here to compress the system. So the change in thermal energy here is less because this delta T is less. It is always equal to this equation, but then there is the added work. Remember, delta E thermal is equal to Q plus W. In this process here, we don't have W. In this process here, we do have a work being done, and that is the reason we are going to have a temperature greater than 20 degrees.